And we'll start from current slide. I may have said it before. Any questions on anything we've covered so far? Okay. Where my memory was, a long time ago, a week ago, where we left off, we had done the A part here, and we were just about to do the B part, and we ran out of time. So, anyone remember? Finding the zeros of a function. How do we do that? What do we mean by the zeros of a function? We're doing the B one here. G of x equals square root of 10 minus x squared. How do we do that? Set it equal to 0 because the function is g of x. Ooh, that's funny. And we want that to be 0, so just set this equal to 0. And since g of x is square root of 10 minus x squared, we will, let me get my pen set up. Okay, we'll do the square root of 10 minus x squared and set that equal to 0. All right. Now, what's the next step? Say again? Radical sign, exactly. How do we do that? Erase it? Oh, I'm sorry.
Square.
Yeah, square both sides, which is almost, in this case, like erasing it. Because when you square 0, you get 0. Now, here's a little warning. Anytime you square both sides of an equation, this one's not going to hurt us any, but anytime you do this, you really ought to check your answers and make sure they work, because sometimes squaring both sides of an equation will introduce what they call extraneous solutions, solutions that look like they're right, but really will not be. So it's a good idea to check. But if you square both sides, what do you get? Help me? 10 minus x squared is equal to 0. It's almost like we did, just erase the radical. Now what do we do? Second? Okay, let's see if we can factor this thing. If we can, what would that be? Anyone? Okay, we squared both sides. When you square, I'll actually write it down. Okay? We squared this, and we squared that. Okay? And when you square a square root, you lose them both. You use the square, you lose the square root. When you square 0, you get 0. 0 times 0 is 0. Okay? It was magic was the answer, really. Yeah, we did it. Okay? Now, I heard factoring. If you've worked at this a moment, you'll see it will not factor using integers, but you can sort of still factor it if you want to. Did you want to, or try something else? Yeah. Okay. Well, this is a difference. And this one's a perfect square, obviously, right? That's not a perfect square of an integer, but it is a perfect square of an irrational number. Know what irrational number that might be? This. How do you undo a square? Take a square root. So you could say this is the square root of 10 squared minus x squared. You asked for it, you got it, Toyota, okay? All right, and this is Q, right? Okay, and help me? Huh? Mayfield, okay. Candria, right? Okay, and Q is there. Okay. All right, anyone else come in? I did not mark you. Oops, one more. And what? McMillan, got it. Dion, and, oh, Tell. Okay. Anyone else come in since I called roll? Okay, good deal. Well, no skiing accidents so far. Okay, that's good. All right. So now we have, in a sense, the difference of two perfect squares. It's not really a perfect square, but it is a square. Okay? So what do you do with that? Can you factor the difference of two squares? Yes, how? Say again? Thought I heard something. Help me. How do you factor two squares? If you had a squared minus b squared, how does that factor? Say again? I'm sorry. Okay, now that is a possibility, okay? But we were choosing factoring. That would be factoring doing that way. That'd be solving for A or B. Yes? That's exactly right. It factors as A plus B times A minus B. Okay, we know that. Now, here our A is square root of 10. And then, we actually got it. Okay. Thank you. I was just going to make my way around there to do that. I needed to write his name down before I forgot it. Okay. All right. So what we have here is our A is the square root of 10 plus x. You see? Just have these following that times, what was the next part? Help me, help me. Square root of 10 minus x. And that's equal to 0. All right, we factored it. Now what do we do? Boy, it was a long week. Yes? Huh? Okay. If two entities are multiplied giving you 0 as a result, one of those entities has to be 0. Maybe both, but at least one. So this will be square root of 10 plus x equals 0, or the square root of 10 minus x has to be equal to 0. One of the others those have to be true, if not both. Okay? So, what do we do with that first equation? Say again? Okay, subtract root 10 from both sides. Okay, and what does that give you? X is equal to negative the square root of 10. And on the other side, we'll? Say again? Okay, how about, I like what you're saying first, how about let's adding x to both sides? That's a little easier. And what does that give you? X equal positive square root of 10. Okay, and like I said, anytime you square both sides of an equation, good idea to check your answer. In fact, it's a good idea to check your answer anyway. So let's see, if we put a negative, oh here it is, negative square root of 10 in for x, what's negative square root of 10 squared? Negative square root of 10 squared. 2. Square root of 10. Wait, no, you're right. 10. You're absolutely right. And 10 minus 10 is? 0. 0. And square root of 0 is? 0. So let's do positive square root of 10. What's positive square root of 10? Squared. 10. 10 minus 10 is? Yes, they both work here. We didn't think that was going to give us a problem. It didn't. Okay? So, let's move on to the C part. I'm going to erase this. Everybody got it? All right, to erase. Then let me erase this, and let's do the C part. H of t is equal to 2t minus 3 over t plus 5. Now, don't think they require it in this problem, but it's always a good idea. What's one thing that strikes you when you see that function? Okay, it's it's a rational function. It's division. And what can you never have with division? Then 0 in the denominator. So let's take care of that first. It's not crucial to the problem, but it's always a good idea to do that. So what I just said, t plus 5, that's the denominator, cannot equal 0. Right? Everybody agree? Because you can't divide by 0. Let's solve that inequality. And what do we get? How do we do it? Subtract 5 from both sides. And that tells us that t cannot equal minus 5. So don't even put down minus 5 as an answer. It can't ever happen. Okay, now we'll proceed with what they're looking for. Finding the zeros of the function. Okay, we just have to keep in mind t can never equal negative 5. So how would you find that 0? All right. I think I can find these two. Cole and Ryan. And you'll realize I'll probably go through the whole term and never know which one of you is which. So, okay, never mind. Okay. So, what would we do? Finding the zeros of that function. We're on C now. What would we do? You told me before. Second? Set it equal to 0. So we'll do 2t minus 3 over t plus 5 and set it equal to 0. Okay? And can I get your name, please? Alana. Got it. Mitchell, right? Okay. Does anyone else come in since I called roll? I'm not sure I got you. Now, some people find it hard to see over there. You okay? Okay, because there's some more visual friendly places if you want them. Okay. Well, we got a huge crowd today, but I think we can find a seat. Okay. Now, there's a couple ways you can proceed here. What would you like to do on a problem such as that? Second? Okay, what are you going to multiply? Multiply by the denominator. Why do you want to do that? Because she doesn't like fractions. You know, she wants to get rid of that denominator. I know, you can make up any other reason you want to, but I know the real thing. Okay, multiply both sides by t plus 5. Okay? And what that does is wipe out the denominator here. Now, why can we do that? One thing you never do when you're trying to solve an equation is multiply both sides by 0, right? That'll wipe out all meaning of your problem and you don't get a reasonable answer, okay? But we've already said t plus 5 cannot equal 0, so we're not doing that, okay? We're not doing that, okay? Now, what do we have now? 2t minus 3 is equal to? Say again? 0, because 0 times t plus 5 is still 0. Now, we got a pretty easy thing to solve, don't we? And what would that be? How would we do it? Add 3 to both sides, and then 2t is equal to 3. Divide by 2, and you get t is equal to 3 over 2. 3 halves, 1 1/2, and that's not equal to negative 5, so we're in the clear, okay? If that had been negative 5, no answer, okay? But now here's another way you can approach this problem. Your way was perfectly fine. I think that's the way the book did. But here's basically how I look at it. Without this here and that there, I look at this, say this is a fractional form, equal to 0. Now how's the only way that fraction? Can anyone give me a fraction that's equal to 0? Make up one. 0 over 1, 0 over 25, 0 over 5 million, 0 over negative pi, 0 over anything is going to be 0. So the only way you can get a fractional form to be 0 is if the numerator is 0. So what I would do in that original thing, I just take this and say that has to be 0. Go right to this line here. Saves me a step, and I'm really lazy. Okay. So, but the way you did it was perfectly correct. I think it's the way the book did it as well. Okay. As long as that denominator is not 0. Okay, can't have that. All right, and we get t equal 3/2. Not a bad idea to go on and plug it in to see. What's 3/2 times 2? 3 minus 3 is? There it is, and the denominator is not 0. So yeah, we know that is a 0 for the problem. Okay, let's clear my scratch out of the way. Anyone need it up there a little longer? Anybody? Okay. Let's clear that. And let's see, they're going to go over the first one too. I think we already did it. So I know y'all remember this from last week because it was only a week ago. To find the zeros of a function, first set the function equal to 0, which is exactly what you did, and solve for the independent variable, which in this case is x. Now remind me, how would we do that? We set it equal to 0. How do we solve for x in this problem? Say again? Factor, exactly, because this is a quadratic or higher. That's what our first step is when the exponent is 2 or more. Okay? See if we can factor. Can we factor that? Yeah, we went through that before. Remember, we'll just watch them. 3x minus 5 times x plus 2. Let's just check and make sure they factored it right. Certainly 3x and x makes this. Minus 5 and plus 2 makes 10. Let's see if the middle term's right. 3x times x is 3x squared. Yep, that gives it. 3x times 2 is 6x. Minus 5x is plus x. And then minus 10. Yeah, we got it. Okay. Now what do you do? Yeah, so each one equal to 0, because the only way you can have a product of two entities equal 0 is for one or both to be 0. So we first set 3x minus 5 equal to 0, and then they skip the steps, add 5 to both sides, divide by 3, you get x equal 5/3. Okay, that would be a fun one to check. We did, didn't we? And then the other one is x plus 2 is equal to 0, subtract 2 from both sides, x equal -2. And that one's a lot easier to check. Okay. All right. And let me get my book. Remind me your name.
Carla.
Carla, got it. Okay, I know you're in here. You can't hide. There you are. You were hiding. Okay. All right. Anyone else come in since I called roll? All right. Now, here is actually a graph of that function, and we'll see what we mean by the zeros. This is a graph of f of x equal 3x squared minus x plus x minus 10, and because there's no dot at the end of this, it goes on indefinitely in those directions. That is a parabola, and we're looking for the zeros of the function, so that's where the function's equal to 0, and where the function's equal to 0, the function, this is f of x. What is f of x always equal to? Y. And the y is 0 will be on anywhere on the x-axis, because here the y is positive going this way, negative going that way, 0 right here. Find where the function intersects the x-axis. Okay? Now, we also call those the x-intercepts, because the line intercepts the function at those 2 points. Here was our -2, and here was our positive 5/3. Okay. So yeah, that confirms this one did have 2 solutions. Now, just a little hint. Anytime you have the maximum exponents of 2, the most zeros you can have is 2. You may only have 1, or you may have none. But the most you can have is 2. And since you found 2, stop looking. These things are going to keep on going up. They're not going to come back down and have any more zeros anywhere else. They can't. Maximum number of zeros 2. We found 2. Done. Now you might ask yourself, when could that ever have 1 solution? And only 1. Okay, let's just imagine we elevate this parabola up to here until the minimum point. See, as we elevate it, then these will be our 2 zeros, these will be our 2 zeros, these two, they keep being 2 zeros until that single point down here, the vertex they call it, touches the x-axis, and that's all. Then you only have one solution. Okay? It will be a double root, but it will be one. How about no solutions? Keep on elevating. As soon as you get that same parabola up here, then it doesn't intersect the x-axis at all. No solution. No real solution. Okay? So what you're doing is a vertical shift. Okay? If you add whatever this number is here, looks like about 9 point something another, to this, then you would get it up so you have one and only one solution. Add 10 to it, and you won't. Am I saying that right? Add 10 to this. Yeah. Then that new function would be 3x squared plus x. Yeah, that doesn't look like that's going to work. I should have even gone there, should I? Okay. Add enough to it, and soon you won't get any solution. Oh, yeah. We'll just leave that alone for now. Stepped off into something I need to wipe my feet. Okay, how about this one? This is one we just did. Now, we did it one way. We squared both sides, and that's how they're going to do it. Okay, and then we factored, and we factored using radicals, right? I want to show you another way to do it once you got this far. Okay, what you can do is add x squared to both sides. Okay, and that gives you x squared, I'm swapping sides now, is equal to 10. And what can you do to solve that one? Take a square root of both sides. So you take a square root of this and a square root of that. Oops. And what's the square root of x squared? X. What's the square root of 10? Plus or minus, you're absolutely right. That's the danger of doing it this way. You forget about the plus or minus sign. Anytime you take the square root of both sides of an equation, you have to interject the plus or minus on the numerical part. It doesn't do any good to add it to the x. You wanted to isolate the x. Put the plus or minus with that. That's how you get your two solutions there. Okay? And without that, you have problems. Okay? So, that gave us the same solution we did before, if you recall. So let's clear that. And this is exactly how they did. They squared both, they added x squared to both sides, took the square root, but they remembered to put the plus or minus in front of the radical. You always have to do that when you take square root of both sides. Okay? Zeros are then this. Now, anyone know what shape this is? I called the other one a parabola. Is that a parabola? No. Okay? Anyone want to hazard a guess what that really is? Half of a circle. Is a what? Half of a circle. Exactly, sometimes called a semicircle. Okay? And how could you tell that? Well, you see this. Remember, we said this was the g of x. What's another name for that? Y. Why not? Okay. If you wrote this as y is equal to the square root of 10 minus x squared, and then what would be the first thing we would do to clear out the ugly part there? Square both sides. So that would make a y squared, and you lose the radical. So y squared is equal to 10 minus x squared, and then add x squared to both sides. X squared plus y squared is equal to 10. I can't write. Okay. Okay. Now, guess what? That's the equation of a circle. Okay? Because if your two coefficients are the same, okay, and these are both squared, these coefficients here happen to be 1, plus sign in between, whatever this is, you want to know what 10 is in that case? X squared plus y squared equals what? It's 10, but it's the radius squared. X squared plus y squared equals r squared. That's your general equation for a section. Okay, x squared plus y squared equals r squared. And so the r squared is 10, so 10 must be the square root of r. No, r must be the square root of 10. Okay, yeah, that's what I meant to say. And so the radius is square root of 10, and sure enough, square root of 10 is between what two integers? Square root of 10 is between what two integers? You may have said I couldn't hear.
2 and 4.
Not 2 and 4. Well, yeah, it is between 2 and 4. Closer, between 3 and 4. Also square root, okay. Square root of 9 is 3, and the square root of 16 is 4. So it's between 3 and 4. Okay? Because 3 squared is 9, 4 squared is 16, 10's in between those two. Closer to 3, so it's 3 point something another. And sure enough, that's what we got. Now, is this a function? Is this expression right here a function?
Yes.
No, this expression would be a complete circle. Would that be a function? No, that's why this is a function, because that's only the top half. You could put a minus sign in front of it, and then you'd have the bottom half of the circle. It has to be semicircles, because a circle is never a function. Nice, beautiful graph, but not a function because it fails the vertical line test. A little bit of review here. Okay. Any questions on that? All right, let's go to C. And first thing we do, set the function equal to 0, which we did. And then they multiply both sides of the equation by t plus 5. They didn't show it, but they did it. Left you with the numerator equals 0. Because t plus 5 times this wipes this out. T plus 5 times that stays 0. Or, the way I think of it, is the only way this fractional form could be 0 is the numerator 0. You get to the same statement right there. Okay. Either way you want to do it. And then this is easy to solve. T is equal to 2. Well, this time they do all the steps. Add 3 to both sides and divide by 2. So T is equal to 3/2. Now, are they going to draw a graph of that one? Yes, they do. Okay? And here's what that one looks like. Okay? 3/2, 0. Again, the x-intercept, just like the last one, I didn't point that out. That's where the graph intersects the x-axis. Now, you might ask yourself, is that all there is to this graph? And the answer is no. Okay? We have it done, what we call this is a rational expression. It's the ratio of two polynomials. We haven't even defined what a polynomial is yet, but you probably know that from before. And what you have here is a situation. Remember the first thing we did with this? First thing we did. That, yeah, the denominator can't be 0, and what did that produce?
T is not equal to -5.
T is not equal to -5. So what we would do then, if we were really graphing this, I would come here and get my cursor to be red again. Well, let me leave it black for just a little bit longer. Okay. Extend my x-axis here a little bit, and then put, what, that would be a -6 right here. So then I would, if t cannot equal -5, here's -5, and it can never, ever, ever equal. And sure enough, this function's going down, 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 but never crossing or even touching t equal -5. Okay? So your vertical asymptote, that's what that's called. It's a vertical line. Function can never touch it because t cannot equal -5 anywhere, forever, up or forever down. All right. Now, we haven't done this yet, and you aren't responsible for it, but to get what we call the horizontal asymptote, what that is, where are the functions going in the long run for very, very large values of t. T is your independent variable here. Well, what you do there is look at, for large values of t, the leading terms take over. Who cares about the -3 and -5 when t is a huge number? 4 million or something, plus 3, minus 3 or plus 5 isn't going to make much difference, okay? Only the leading terms are going to win here. So what we do is look at the ratio of the leading terms. And what's the ratio of 2t over t? 2, okay? That's your horizontal asymptote. So I'll take this. Now, I don't have to have this one read, okay? Let me get your name, please. One more time. Okay, got it. Maisha? Okay, got it. All right, my hearing's so bad I can't distinguish. So at y equal 2, that's your horizontal asymptote. And sure enough, let's go back to our function here in black. See, this is going up, approaching 2. Now, a function can touch or even cross a horizontal asymptote, can never touch a vertical asymptote. So this is going to keep on heading down south here, getting closer and closer and closer and closer and closer and closer, but never touching t is equal to -5. On the horizontal, it's approaching, and this one won't ever touch y is equal to 2. Okay? That's the horizontal asymptote. Now that leaves a whole lot of space over here. If you were to come over here like to -6 and plug in a -6 here, this would give you a -12 minus 3. That's going to be -15 over -6 plus 5 is a -1. -15 over -1 is 15. So this is going to be at -6. This is somewhere way up here at 15. So guess what? This one's going to look just like that, mirrored across here, and just look just like that. So there's the other side of your equation. But guess what? We're interested in x-intercepts, or where the function is equal to 0. Never going to be equal to 0, because this, again, gets closer and closer to 2, but never, I have it touching. It's not going to touch. It'll get closer and closer to, you see, I drew the line too high. It should be down here. It'll get closer and closer, but never touch. So there's no way it'll ever intersect the x-axis, ever. Okay. So that is our one and only. You didn't need to know that, and I know you'll sleep better tonight knowing it, though, right? Yes, okay. Good deal. Any questions? All right. There is a checkpoint, bottom of the page. Please do those as soon as you can. If you have trouble with them, there's audio-video solution for those checkpoints in both English and Spanish at larsonfreecalculus.com. Any questions? All right, let's move on to increasing and decreasing functions. What in the world would we mean by that? What would you say about this function I just drew here? Increasing or decreasing? Say again? It's increasing over here, isn't it? Because even though it looks awfully flat out here, it's always moving up just a little bit, just a tiny bit. Then up here, it's obviously increasing. But what's it doing on this side? Way increasing here, and then getting closer and closer and closer and closer. So it's slightly increasing out here. So this one's increasing everywhere. Make sense? Okay? Just jump back. Not too high. Okay, how about this one? Increasing from -√10 to 0, because we always measure that on the horizontal axis. X equals -√10 to x equals 0. It's increasing, but from x equals 0 to √10, it's decreasing. All right, y'all already got the idea. And we haven't even covered it yet, okay? How about this one? Decreasing from -infinity, because this one just keeps on heading up. Remember, from -infinity all the way to whatever point that is. Now, I don't know what it is. It looks like 0.2 or something like that. And at some point there, then from there on, it's increasing again. So there we have what we mean by increasing and decreasing function. What is the y values doing when x is increasing from left to right? Okay? So we already covered it, right? Okay. The more you know about the graph of a function, the more you know about the function itself. So the graph is just another way to represent a function. Here's a graph here, a rather bizarre one. This is a piecewise defined function. As you move from left to right, remember the x is always, x always going from left to right, then what's this function doing? Now this one is only defined from -2. How do you know that? There is a closed circle here. There's no more function up here. It's only defined. This has a explicit domain from -2 to +4. Yeah, okay. Only defined there. So where is it decreasing? From -2 to what? Decreasing. -4 to -2 to 0. You talk about where the part of the domain, the x values, the horizontal values, it's decreasing from x equal -2 to x equals 0. Then what is it doing beyond that? It's constant, neither increasing nor decreasing from 0 to 2, and then increasing from 2 to 4. Got it. Now, when you're talking about these intervals of increasing, decreasing, or constant, you don't need to worry about, well, is the endpoint included? Is -2 included? We don't care. Okay, so we usually use parentheses only from -2 to 0 in parentheses, from 0 to 2 in parentheses, and from 2 to 4 in parentheses. Oh, it's hard to tell whether that's decreasing or constant there. I mean, that's the turning point, so we don't really worry about it. And the starting points we don't need to worry about either, okay? Or the ending points, okay? So this is what we mean by that. You can either be increasing, decreasing, or constant, okay? Easy to see on a graph, isn't it? Pretty much, okay? Here's how they do it in words. Boy, I like seeing it on a graph better, but this is what we mean in the words. A function is increasing on some interval when, for any x1 and x2 that are in that interval, if the x1 is less than the x2, the x1 is less than x2, the function is increasing. That implies that f of x1 also is less than f of x2, because as you go from left to right, the function is going up. So that's what we mean by increasing. The function f of x1 also has to be less than f of x2 for every x1 and x2 in that interval on which it's increasing. Now, if it's decreasing on some interval, when for any x2, any x1 and x2 in the interval, as long as x1 is less than x2, that implies that the f of x1 has got to be greater than the f of x2 for this to be a decreasing function. Not greater than or equal to, greater than. Same thing up there. That's the decreasing function. And a function is said to be constant on interval for any x1 and x2. Doesn't matter the order, f of x1 is equal to f of x2. Always. No matter which two values you choose on that interval, they're always equal. Then it's a constant function. So that sort of makes sense. A lot harder to visualize though. Graphs are great for that. So let's say what's happening here. This is example 4. We haven't skipped any, have we not? Make sure I didn't skip one on the previous page. No, we didn't. Okay. What is this function doing? F of x equals x cubed. So what? Increasing everywhere from minus infinity to positive infinity. See, this has no limits on it, so it's increasing everywhere. Now you might say, hey, well, wait a minute. How about right close to 0? That looks pretty flat to me. Well, let's try some values. So give me something pretty close to 0 but slightly negative. Make up a number. Real close to 0 but slightly negative. Negative what?
1.
Negative 1. Okay, that's way over here. Yeah, you're down here at -1. Even, huh? 0.1. Okay, negative 0.1. Cube that and what do you get? Negative 0.001. Okay? It's really close to 0, but it's still slightly negative. Okay? And you can get closer and closer and closer, and you're getting closer and closer to 0, but you're not quite 0. Still slightly negative. Only place at 0 is at 0, and then slightly past that is slowly, slowly, slowly increasing, but is increasing and soon takes off and goes. So that is increasing everywhere. Even though it looks pretty flat there, it's not actually flat. All right, how about this next one? Okay, increasing from negative infinity to -1. Next, decreasing from -1 to +1, and increasing from 1 to infinity. Perfect, perfect, perfect. Okay, always give the intervals of increasing, decreasing as your x values. You look at the y values, but you don't really worry about it. Okay, how about that third? Increasing from where? Negative infinity to 0. Then constant from 0 to 2, and decreasing from 2 to positive infinity. Perfect. Y'all are good at this. Really, really good. Okay? The strange thing is, in your book, they have different examples. Okay. They have one that looks like this is the A part, one that looks like this is the B part, and one that looks like that is the C part. So, no wonder you had to buy a new edition so they could rearrange the problem for you, okay? That was worth the money, wasn't it? Okay, I'm just kidding, kind of. Okay. There is a checkpoint at the bottom. Please do the checkpoints. Any question? Increasing, decreasing, constant functions. Anyone need it a little longer? Okay. Oh, they're going to tell us what the solution is. The function, first one was increasing of the entire real line. That's from negative infinity to infinity. The second one was increasing on the interval from negative infinity to -1. Decreasing from -1 to 1. Exactly what you said, increasing from 1 to infinity. Okay, and C, the function is increasing on the interval negative infinity to 0, constant from 0 to 2, and decreasing from 2 to positive infinity. Perfect, perfect, perfect. Okay. To help you decide, look like you needed any help, decide whether a function is increasing, decreasing, or constant on an interval, you can evaluate the function for several values of x. That's what I said doing when you weren't sure about that one that looked pretty flat at the origin, but you found out it was. However, you'll need calculus to determine for certain all the intervals on which a function is increasing, decreasing, constant. We're looking forward to that, aren't we? Yes, okay, when we get to our calculus. Hopefully many of you will. I doubt it, but hopefully you will. Okay. So let's see. The points at which a function changes its increasing, decreasing, or constant behavior. Those can be sort of important points too. They can be your relative minimum, because if it's decreasing here, changes to increasing there, somewhere down there you got a minimum value, right? And if it's increasing here and then decreasing there, somewhere up there, you've got a relative maximum. Okay? So that's what we're talking about for these values. So if you know where they're increasing and decreasing, then you also know where your relative minimum and maximum are. Let's just go back to these others and see. Okay? What would you say about this one? Relative minimum or maximum? Neither. Okay? This is because it's increasing everywhere. It can't have a minimum. It would be over at negative infinity somewhere, which is a number. And the relative maximum would be at positive infinity, which is a number. It just keeps on climbing. So this one doesn't have a relative minimum or maximum. That in there is not, because it's still slightly increasing throughout. How about the next one? What would be your guess? Okay, and where? In which?
Would you look at X and Y?
Okay. Relative maximum at -1, 2, and relative minimum at 1, -2. Now, if you've been wondering why I kept saying relative rather than saying maximum min, this isn't a maximum here because guess what? The function is way bigger over there. But close to it, this is a relative maximum. Okay? And the function is much less back this way than this one, so this is just a relative minimum because anywhere close by, that's the minimum value. Not forever. Okay? That would be absolute maximum or minimum. Now this one's a little bit bizarre. It has relative minimum anywhere along there. Okay, because never does it get any higher than that. Okay, it does get lower here and here, but never any higher. So these are all relative maximum values here. That entire line from 0 to 2. That's a bit bizarre. Let's see if that really does fit our definition. Here's the definition. A function value f of a. That means pick an a somewhere on the x-axis, then the f of a is the y value for that, right? That f of a is a relative minimum. So you notice that the y value is called the relative minimum of f when there exists on some interval x1 and x2. When they write it like this, x1 has to be less than x2. That contains a. So in other words, x1 is to the left of a, x2 to the right of a. A just is anywhere in that interval, x1 to x2. A is somewhere in there, okay? This interval contains a. Such that for x1, always less than some value x, less than x2. That means x is in that interval. Implies that the f of a is always less than, this is a relative minimum, or it could be equal to any of the f of x's in there. Okay? So therefore, that flat part, they would be equal to it, so that would still be considered in that case, a relative maximum, not a relative minimum. And similarly, a function value f of a, pick an a somewhere on that function, and f of a is a relative maximum of f when there exists on an interval. See, that's what the relative means. You find some interval, even though over here it may be max, or over there it may be more, on this interval, this is the closest, the highest value you have on that interval. x1 to x2, so that contains a has to be in that interval. Then for any other x in the interval, between x1 and x2, every other x there implies that f of a is always greater than, or it could be equal to, all your rest of the f of x's. And that's why from 0 to 2, those are all relative maximums. Make sense? You like to say, what's the big deal? These are just words. These are just things that have us do. No. Any of you going into business, you think at some time in your life. All right. And do you think you might want to make a profit? No, you're going to be egalitarian and just give things. No, you probably are interested in making a profit. And you might even be interested in maximizing that profit. Sure, if you charge more for your good, whatever it is, you should make more money. But if you charge too much, then they aren't going to buy it. They go somewhere else and buy it. Okay? So as you do your cost versus pricing, you get some relative maximum. That's what you're looking for. Unless you just want to give it away. Okay? That would be fine too. I'd like to find out your address of your store. Okay? Never mind. Okay. So, yes, max and min is pretty important. You may want to minimize your cost. You may want to maximize productivity. You may want to minimize absenteeism. I mean, you can think of lots of things that you want to either get the most out of it or minimize, cut the cost. So here we have several different relative values. Now this function obviously continues here, and we don't know what it does here, but we're going to leave it alone. And this continues here. We don't know what it does. It looks like it just keeps heading south. This one looks like it might be turning a little bit, but we don't know. We don't care. As you see here, here's a relative minimum. because for some interval around this value, here's your A in this case right here. Somewhere around that A, I guess I should be, people who are not here watching my finger. So this could be your A here, okay? And for some interval around the A, this would be your x1, this would be your x2, around that, your f of A is always less than or equal to, in this case less than, all your other x's in that interval. Now you don't want the interval to go way out here or go over here, because that may not be the case at all, but you do want it to be close to it. So there is some interval around A that all the other values in here are greater than or equal to alpha of A. Same thing here. You can make this your B. Okay, and pick some x1 and x2 around B, and for all the other values, your f of x1 or f of x, any other value other than B, are always going to be less than or equal to f of B. F of B is up here, all the rest of them are less than that. And again here, this could be your C here, and then pick a x1, x2 around that, and all the other values, f of x is greater than f of C. Same thing here, maybe this is your D, okay? Pick an interval here, and all the values around there are less than or equal to f of D. Does that make sense? So this is, by definition, the graph is so much easier just to look at it and see. Okay? Any questions? And again, important implications in business, economics, medicine, you name it. Okay? You want to minimize exposure. Okay? Maximize coverage, whatever. Okay, you'll study a technique for finding the exact point for which a second-degree polynomial, which we call a quadratic polynomial, has a relative maximum or minimum. We'll do that in the next chapter. For the time being, however, you can use your graphing utilities, you can just plot up the points to find reasonable approximations for those points. Okay? Really nice to have a graphing calculator, but if this is the only math course you're ever going, last math course you're ever going to take, that's a pretty expensive toy to get just for this course. I'll let you decide whether you want it or not. If you're going further in math, you may want one. Okay. Now, next topic here, that was relative minimum and maximum, is average rate of change. I think when we introduced this section, I said, you've done this before, and you probably don't realize it. Average rate of change. Okay? When we say rate, what are we talking about? Can anyone think of a rate you've already used this morning? Second? Fraction. Okay, a rate is a fractional form. Okay? Especially the units are. Did any of you drive here this morning? Okay? When you were driving, did you happen to notice that gauge right in front of you? You probably should have. Okay, what was that measuring? What was that gauge right in front of you measuring? Miles per hour, there's a rate. How many miles, what distance do you travel in a certain time? There's a rate. It's a fractional form. Miles per hour. You're using rates all the time. Okay, so that's what we mean by rate. Something is being a fractional form, a division. Okay, change is happening though, average rate of change. If something's happening from one to another, you have a difference in there. When you have a division, what do we call that? What's the answer to a division problem? Quotient. And when you have a subtraction problem, what do we call that? The answer? That's a long time ago. What do you call the answer in a subtraction problem? The minuend, the subtrahend, and the... Boy, y'all need to go back to grammar school, okay? Your difference.
Oh, yeah.
Oh, guess what? We already talked about difference quotients, average rate of change. Hey, you can hardly tell them apart, okay? We've learned that the slope of a line can be interpreted as a rate of change. If the line's going up there, you're speeding up, you're increasing. If the line's doing this, you're decreasing. Just like we were just talking about on our functional form. Now for a nonlinear graph, the slope changes at each point. Then you talk about the average rate of change between 2 points. Okay? The average rate of change between x1 here and x2 that's an increasing. That'll be a positive average rate of change. If we had brought the x2 into here, that would be a greater average rate of change. If we move it on further here, it would be a lesser average rate of change. And it looks like if we took it here, the average rate of change could now be decreasing. So it varies with what 2 points you choose. Okay? Now, but what tells you that average rate of change is the slope of this line, and we call this line that intersects any curve, any graph at 2 points, we call it a secant line. Never called it that before, maybe, but that's what it is, a secant line. So what is its, and this is a function now, what is the slope of a line? From way back, rise over run. The rise is your change of your vertical values, your y values, and the run is the change of the x values. But what do we call the y values in a function? What is y? F of x. So this would be, if this is x1 and x2, this would be f of x1 up here. This is f of x2 up here, f of x1 here. So this would be f of x2 minus f of x1 divided by x2 minus x1. That's your difference quotient, average rate of change. Same thing. Same thing as we had before. That's what average rate of change is. So a line through any 2 points is called the secant line. The slope of that secant line is denoted as m, the slope. Where that comes from, I don't know. And subsecant, SEC standing for secant, not Southeastern Conference. Okay. The average rate of change from x1 to x2 would then be the slope of that, which is y2 minus y1, which is f of x2 minus f of x1 divided by x2 minus x1, which is exactly what our average rate of change was, which our difference quotient was in the last section. Change of y over change of x, that's the slope of your secant line. Make sense? Okay. Doesn't matter how squirrely the function looks, pick 2 points, find the average rate of change. So here is a squirrely function, okay? Find the average rate of change of this function, f of x equal x cubed minus 3x. And we're going to do this from x2 equal negative 2 to x1 equal negative 1. I've said it backwards. x1 equal negative 2 to x2 equal negative 1. So how would we do it? What would be your average rate of change? Average rate of change. I'll probably soon call it ART, average rate of change. ARC, whatever. Okay. Well, how is that defined? From this point to that point. Okay. Now, let's just imagine they didn't give us the graph here. It's just way too easy with the graph. If they didn't give us the graph, what you would do here is plug in. Oh, you give me the formula for average rate of change. Let's do that first. Say again? F of x2 minus f of x1 divided by x2 minus x1. Okay. So the first thing I would do then is figure out what f of x2 is. Well, what's your x2? Negative 1. So instead of x here, we're going to plug in negative 1. So your f of negative 1 would be what? Here's your f function. What does f of negative 1 be? This is f of x2. Say again? You may have said it. I was talking. What was it? Negative 1 cubed minus 3 times negative 1. Okay? Negative 1 cubed is negative 1. Minus 3 times minus 1 is plus 3. So the alpha of minus 1 is 2. Got it. And look there. That's how we got the 2 there. Okay? Now, then do alpha of x1. x1 being negative 2. So what would be alpha of negative 2? Yuck. I can't write. That would be what? Alpha of negative 2? Negative 2 cubed minus 3 times negative 2. And what would that give you? Negative 2 cubed is? Negative what? Negative 8 is 2 times 2 times 2, only they're all negatives. And this would be negative 3 times negative 2 plus 6. So this would be negative, say again, 2, right? Okay, I couldn't hear. And that's how we got this negative 2 down here. Okay, so now we got everything we need. The average rate of change between those 2 points is alpha of x2, which would be 2, minus alpha of x1, which would be negative 2, minus a minus 2. Okay, all these signs, keep up with them. And the x2 we already knew, negative 1, minus, and the x1 was, we lost it. Okay, x1 was negative 2. Okay. I'll sit down so y'all can see over me. Now I can't see. Okay. So what's 2 minus a minus 2? 2 plus 2 is 4. You got high level math today. Minus 1 plus 2. And 2 plus 2 you said was 4. And minus 1 plus 2 is? Second? 1. So this is going to be average rate of change of 4. Yeah, that's a pretty steep line right there. Slope of 4. Does that make sense? All right. There was the A part. Let's do the B part. Okay, do I want? Yeah, I think I want. No, I don't want to erase it all. I want to erase most of it. This time we're going from, oh yeah, I want to erase it all. Okay. Okay. Let's erase it all. Okay, this time we're going from x1 equals 0 to x2 equal 1. So we're looking for average rate of change. What was that formula again? Alpha of x2 minus alpha of x1 over x2 minus x1. So what's the first thing we've got to calculate? Alpha of x2. And what's your x2? Of 1. And what's alpha of 1? 1 cubed minus 3 times 1. And that would be 1 minus 3, which is negative 2. And that's where they got that negative 2 right there. Okay? Next thing you need to calculate, alpha of x of 1. Right? Okay, that's this one right here. We did the first one. And what is x of 1? 0. Oh boy, I think I can even do that one. What would that be? 0 cubed minus 3 times 0. And what's 0 cubed? And what's 3 times 0? 0. And 0 minus 0 is? 0. That's how they got the 0 right there. 0, 0 is on your curve. Okay, I think we're ready to roll. And what's our average rate of change? Alpha of x2 was negative 2 minus alpha of 0 was 0 over 1 minus 0. What does that give us? Negative what? can't just have a negative.
Negative 2.
Negative 2 over 1, which is negative. So that's going downhill pretty fast. Not as fast as the other one's going uphill, but still pretty fast. Does that make sense? Average rate of change, same as your difference quotient. Take a difference of your numerator, difference of the denominator, take the quotient of the two. Make sense? Any questions on it? Let's see how they do it. I think I'll just go to a new slide. Yeah. Average rate of change. I'll try to stand up again. Hard to read down there. Average rate of change from x1 of negative 2 to x2 of negative 1 is f of x2 minus f of x1 over x2 minus x1, which is f of negative 1 minus f of negative 2 over negative 1 minus a minus 2. Okay? Now, we calculated what f of minus 1 was as being 2. You could have looked on the graph, but we calculated. Minus f of negative 2, that was negative 2. And then minus 1, minus a minus 2 is minus 1 plus 2. That came up 1. So that would be 4. Secant line has a positive slope, 4. Pretty steep. Okay? The next part, you're going from x1 of 0 to x2 of 1. The f of x2 would be f of 1. You have minus f of x1 would be f of 0. And that would be over x2, which is 1, minus x1, which is 0. Okay? There's your average rate of change, which is your difference quotient. Okay? And you figure what that is. F of 1 was negative 2. F of 0 was 0 divided by 1. That would give you a slope of negative 2. So there it was going downhill pretty fast. Not as fast as it was going uphill before. But there's your average rate of change between those 2 points. Does that make sense? All right. Now, I think we got time for example 7. They don't show example 7 on the slide set, so let's us do it. Okay? Do it to it. Okay? Finding average speed. The distance s in feet in a moving car from a stoplight is given by this function. S of t is equal to 20 t to the 3/2 power. Oh my goodness, what do we mean by 3/2 power? Anyone know? T to the 3/2 power. Your calculators will do it if you know how to enter it, and you won't even need to know what you're doing, okay? It's a problem with calculators. What does it mean, something to the 3/2 power? Well, the numerator, as you would expect, is just an exponent. What's the denominator? That's the index of a root. So this is the same as saying 20, and there's 2 ways to say it. I'll give you both of them. For some reason my 0 did not write. Okay, there it is. 20, and it's going to be t cubed, but you're taking the square root of it. Now with a square root, you don't have to put the 2 in there. But if this had been to the 5/3, then you'd have a 5 here and a 3 right there. Okay? But this is so that's one way to write it. Another way to write it is this way. 20 times the square root of t. There's, you put the square root first, and then you cube that answer. Both of those will give you the same result. So it doesn't really matter. Most of the time, it's easier to take the square root first and then cube it. That keeps your numbers smaller. Not always, but most of the time it does. So that's what we mean by t to the 3/2. All right, where t is a time in seconds. It says find the average rate of speed of the car from t1 equals 0 to t2 equal 4. Are we going to have time to do it? I don't think so. Sorry about that. Spent too much time explaining what it was. So we'll start next time finding average speed. Okay? Now, but before you go, oh yeah, we don't want to miss this part. We're almost through with section 1.5. We'll finish it next time. Homework exercises here, either 7 or 9 or both. They're both at Calc Chat, 9's at Calc View. either 11 or 13, they're both at Calc Chat. 11's at Calc View. Any of the odds 15 to 25, they're all at Calc Chat. 25's at Calc View. Any of the odds 27 to 31, they're all at Calc Chat. And any of the odds 33 through 39, they're all at Calc Chat. 35's at Calc View. Any of the odds 41 to 47, they're all at Calc Chat. There's a fractional exponent there. Any of the odds 49 to 53, they're all at Calc Chat. 51's at Calc View. I think you can do any of the odds 55 to 59, they're all at Calc Chat. 57's at Calc View. Then do either 61 or 63 or both. They're both average rate of change. They're both at Calc Chat. 61's at Calc View. And we'll worry with the next ones later. Good deal. Another paper in. Excellent, excellent, excellent. Squeaked in by the bell. All right. I've heard this song before. Yeah, okay.
I have it. I need to print it out.
Okay. All right. Good deal. All right. Good deal.
So,
I just said this, but have a good weekend. I mean, last time we met, I told you to have a good weekend. Okay. Yeah.
I tried to access the book and the same days, but it says I have to pay like $50. I already paid $119.99.
Okay.
I purchased that plan from bookstore.
Okay.
But when I search the book,
Right.
it says I have to pay $50. I got my English book for free
Yeah.
because I paid $120.
Okay. Did you have to enter any codes for the English book?
Yes.
You did. Okay. Well, you probably need to enter a code for this one, then it will be free.
But I purchased $120
Huh?
I purchased the plan.
I know. I don't know why they do it, but sometimes they do.
So
Yeah,
what I do?
Yeah. They said they're going to get me the codes. I asked for them earlier. They didn't give them to me, so they still say they're going to get them to me. So I hope to have them. They may have even come in my email yesterday. I didn't get a chance to check it last night, so I'll check it probably tomorrow. As soon as I can. Hopefully by Tuesday I'll have the codes.
So I can just enter it.
Huh?
I can just enter the code.
I guess so. What code did you enter for your English book? Something your instructor gave you, or was that something off your receipt?
You see.
Well, then you should have been able to get the math book too. Go to the bookstore and ask them why they're doing that. I thought you meant you had the, okay. Go to the bookstore and ask.
And I have the paper, but I need
I
to
know,
print
I've
out.
heard that.
So,
Okay, yeah, get them to them. Yeah, okay. Yeah.
Okay, so last Thursday I moved, and now I'm an hour and a half away from here now. And I've been having trouble getting here on time.
Uh-huh.
And I was wondering if there's any class later in the day that I could come to sit in and learn and maybe take quizzes and stuff. Stay in the same morning class. You don't have to change anything.
Right. Well, I don't teach it another time of day. This is the only time I teach it.
Okay.
But I think Dr. Thomas probably teaches a Math 112 class. You can check with her and see if that's okay for you to sit in.
I want to stay with your class.
Okay, you sad thing. Never mind. But, I do record everything, so anything you may have missed, you can listen to it.
Thank you.
Okay. So you kicked them out, huh? Okay. All right. They didn't think that was funny. All right. All right. Let's end this. I recorded all